Oh.
Okay, it's my pleasure to introduce our next speaker. So I'll try to pronounce it correctly. Suddhasattwa from.
I'll do it. A colleague of Jimmy Walker.
Okay.
Ah, that's it.
Who's going to speak to us about avoiding extremes in chaotic systems.
Thank you, Mike, for this opportunity. So, my talk today is about a concept called partial control. So let me explain how it is different from classical control. In classical control, there is a reference trajectory. There are disturbances and there is a control, and we try to make the system follow a reference trajectory. In contrast, in partial control, there is no reference trajectory, but there is a certain bounded subset of the space, some compact region of the space. And because of this relaxed requirement, it is applicable to systems where the control is weaker than the noise. So when my control is weaker than the noise, it is impossible to be asymptotic to a reference trajectory.
Right.
But this is something that we can try to achieve. So I'll directly go to the setup. So these will be the notations that we'll be following for the rest of the talk. So there is some compact region Q, and there is a map from Q to Rx. And after each iterate, a perturbation will be added, which I am denoting by CL. This is a Greek letter C, and it's bounded by a fixed constant C greater than 0. And based on this disturbed value, I am going to add a control. And so these are vectors in n-dimensional space, and these are positive constants. And importantly, we have this, that this is bigger than this. So this is the setup that we are going to use for. So before getting into definitions, let's just look at an illustration. So we'll be looking at these two maps. This is called a tent map. Its slopes are 1.3 and 3.01. So because the slopes are greater than 1, almost all trajectories is clear from the unit interior. Both of these are self maps of the unit interior. But in this map, most of the trajectories is clear. And to give it some context, let's say that these are some economic models. X is some measure of economic activity, and my Q would be this interval. So let's say that if X goes below 0.5, it's a crash in the economy. So this is just the ordinary trajectory without any perturbation or control, and so clearly we cannot satisfy that Xn always lie in this interval.
Sir, is this for the logistic or for the tent map?
Yeah, I said to that. So my illustrations will be for the tent map.
Okay.
And it's also a chaotic trajectory. This is a typical trajectory of the system. And now to this I'm going to add perturbations. The perturbations will be bounded by 0.05. So we see that these so-called crashes are even more frequent. Right? The average value has decreased.
Yeah.
Now, if we try to control this, how good a job do you think they can do? If my U is 0.04, which is lesser than 0.05. So it turns out that we can do a pretty good job. So this is an example of the control trajectory, and this is the dynamics. So these three green bands that you see, these are some specially chosen intervals. And this is my strategy. These three green intervals have the special property that if I start in these intervals, I can always return in these intervals, whatever be the perturbation. So as long as my perturbation is bounded by this, it is always possible to stay within the green set. This avoids transition. And that's why this is called a safe set. This is a very central concept of partial control. So here comes our definition. So a safe set is a subset of Q such that if I start in the safe set and I add a perturbation, I can choose a control that brings me back into the safe set. And my illustration was for a one-dimensional system, but safe sets, this applies for any dimensional system. For example, this is a safe set in the rotated horseshoe map, the regions marked in yellow. So what happens is that if I start in these yellow bands and I am perturbed, I can always come back into one of these yellow regions. Conversely, if I start outside this yellow region, the perturbations can be so chosen that I eventually get out of this box. So one thing about these perturbations is that these are not randomly generated, not necessarily. They could be chosen by an adversary. They could be optimally chosen by an adversary. They are not necessarily random. So here this is a closer example of why those intervals achieve that goal. These three intervals are what we call the safe set. The first iteration carries them into these yellow intervals. Then when I add a perturbation, these intervals get thickened by these red into these red intervals. So the perturbed point will lie in any of these two intervals. But this happens to coincide exactly with this set thickened by u, by the constant u. And these, and these two are exactly the same. Which is why from here I can always come back to it. So this notation S plus U and Fs plus C, these are not vector addition, this is just thickening a set by U. This is an abuse of notation, it's actually a geometric property. So this equation that you see, this is precisely what we were seeing in the previous diagram. A safe set is a safe set. A subset is a safe set if it satisfies this relation. So plus U means thickening by U, minus C means thickening and then retracting the boundary by C. And so this is a defining equation for a safe set. So we just had a look at this example, and as we vary these fixed constants, these also change. So the goal of our work was to investigate how the safe set changes as these parameters are changed. So we see that not only does the measure change, the number of components also change. So this is a bigger picture. So first of all, observe that this axis has the control and this axis has the perturbation. Since u less than c, I don't have any points above this diagonal because u is less than c. And all these white regions that you see here do not have a safe set. There is no safe set for these values. And these colored regions denote the measure of the safe set. This is the color scale that is used. So you see that what we can observe is that the number of components change. In fact, here we suspect that there can be the number of components goes to infinity. Also, there are these curious edges in the diagram across which sometimes a safe set vanishes and sometimes a safe set change is discontinuous. So our work was to investigate how the safe set changes.
The axis on the control goes from 0 to 1, is that right?
No, that's not right. This should be
0 to 0.2?
0 to 0.2. Doesn't.
Yeah.
Thanks for pointing. They should have the same scale as this.
So in some cases, you can make the control, for large perturbations, you can actually make the control pretty small compared to the perturbation.
The ratio can be
Yes,
pretty
you
small.
can.
In fact, the smallest control to perturbation ratio is at this point, is along this edge. In fact, along this point.
Yeah.
So this is this was a previous diagram, and I'm going to look at a slice, a vertical section in this diagram. And this actually gives us all the information that we need. So this is how the safe set changes as C is fixed and the control is changed. So C is fixed at 0.05 and I decrease the control from 0.05 to 0. And around this value there is no safe setup beyond this. So let's see what happens. So we see that we start off with two intervals, then one of the two intervals splits into two smaller intervals. This shrinks to a single point and then there is no more safe. So we are calling these bifurcations, and we call this a split bifurcation and a shrink bifurcation. This is a split and this is a shrink. So then we have this theorem. If f is piecewise expanding, which we saw in the trend map, and piecewise C1, then a bifurcation will occur if and only if either of these two conditions hold. One of the components is a point, or the gap between two adjacent components of S subscript UC is equal to 2. So
Yeah.
maybe I forgot to mention this, but this actually denotes the safe set at U and C, at parameter space. So I'll just go back to the previous diagram. This was the shrink bifurcation, and this was the split bifurcation. This gap that you see is exactly equal to 2U, twice U. And this is also an if and only if. But this only holds for piecewise expanding maps. I had showed you the quadratic map, which is definitely not piecewise expanding. And this is how this is the same plot, the plot of the measure, but for the quadratic map. And if I look at a vertical section of this map, it's more complicated. A lot of other things are happening for non-expanding maps. So this is similar to what we saw earlier. C was fixed at 0.02, and I changed the control from 0.02 and decreased it till the safe set vanished. So for a general continuous piecewise monotonic map, we have this bifurcation structure. So what we need is that it's continuous, piecewise smooth, and piecewise strictly monotonic. Then a bifurcation would occur if and only if either of these four conditions are true. So basically this is a classification of all possible discontinuities in the same set. So these two we have already seen. This is when one of the components becomes a degenerate interval. This is when two adjacent components are exactly equal to 2U. I'll come to this later. This happens when a local maxima or minima of the function lies on the boundary. So this happens right here. Because this quadratic map, this midpoint of this interval maps to 1. So as soon as U is smaller than C, this point is eliminated from the space. which is why we say this. Sorry. And this looks very cryptic, but this is the simplest possible wording we could come up. So this is actually a condition imposed on the boundaries of the safe set. This tracks the dynamics of the map on the boundary of the safe set. So this was our work on classifying the discontinuities of a safe set. So if neither of these conditions are satisfied, not only does the safe set change continuously, the boundaries actually satisfy a differential equation, and that's how we can track how the safe set changes. Any question?
Okay, questions or comments? I'd like to ask a couple questions. First, I observed, why is your tent map non-symmetrical? Is there a particular reason? Because you usually see symmetrical tent maps.
Right.
Was there any reason why that was non-symmetrical? Yet the absolute values of slopes were different.
So,
yeah, that one.
Actually we started our investigation with symmetric tent maps. Symmetric tent maps lead to symmetric safe sets, and so if I computed this same diagram for a asymmetric tent map, I would see less number of discontinuities.
So this only exists in non-symmetric, do I understand you correctly?
These edges are less frequent, but the same phenomena occur. This still happens.
I see.
This still, as long as the slopes are greater than 1 inch for expanding.
Other questions or comments? Okay, I'd like to ask one more question. Could you please elaborate a little more on that? How, that all of a sudden turns chaos into stable cycles? I didn't understand that. Could you elaborate a little more on that, please?
Are you talking about this figure that I...
The safe zone, yes. How does that all of a sudden introduce a safe zone by putting that in?
Right. So these 3 green intervals that you see, these are the same 3 green intervals. So my xn belongs to these 3 green intervals. F of xn would lie in these yellow intervals, and f of xn plus c, this would lie in these red intervals. But all points in these red intervals are within distance u from the safe set S, as you see from this blue figure. That's why I can choose un so that I am back into the green interval. So, if you look more closely at this, so I'm choosing un so that I'm always bringing myself to the nearest available green interval. Right. There's a fixed point somewhere in this interval for the map, and everything above is mapped. So here the map is increasing and here the map is decreasing. So depending on that, so all these points after being perturbed land up somewhere here, and I bring them back. That's how it is.